Now I'm going to hand this off to our What's Up speaker, which is Mike Harms, and he'll be telling us about atmospheric optics. So I'm going to switch off here.
How do you hear me now? Okay.
I should mention, by the way, that if you've got a question for him, for either speaker, actually, I will walk around with this, flag me down, and I'll get to you, because otherwise the Zoom people on the Zoom land won't be able to do it.
Yeah, thanks.
Well,
Okay, hang on just a second here. Whoops. Slideshow beginning. Everybody see that? Yeah, before I get to atmospheric optics, as he was talking about, there's actually a bright supernova in M101 right now. Just was discovered like a week ago. And I happened to notice it online that there was one there, and I notified our friend Jeff Atkins, who's the astronomy teacher over at Deer Valley, and he's got one of these little unistellar telescopes. And so he shot it that night, and the telescope's only like, what are they, 3 or 4 inches diameter? But that's a supernova, and it's a type 2, which means our main speaker can tell you all about it, but it's a big star that blew itself up, basically. And when this picture was taken, it was like 13th magnitude there. Now it's about 10.8. So it's getting much brighter. And so any astrophotographers out there, you might want to check it out. I haven't seen it yet, but I'm going to try to see it. So moving on to our main talk here. Hang on a minute. As astronomers, we look up at the sky a lot, and we even do that during the daytime. And sometimes you see things that are colorful and go, what the heck is that? And how is it, what's happening there? And so I gave this talk like probably 5 or 6 years ago. So I just drug up some of my old pictures that I'd taken over time. So we'll go ahead and start. I'll start by just talking about rainbows here. You can see rainbows from just about anywhere as long as you have the right conditions. And a rainbow is just an optical illusion. We all know that. It's related, when you see rainbows, think water droplets, liquid water. And what you're seeing is the water breaks up light from the sun when it's lit up by the sun. Every water droplet anywhere, if it's out in the sunlight, it's all doing this. You just have to have enough of the raindrops and to be at the right position to see all these various different colors, and a rainbow, poof. And you can even see them at a ballpark. This rainbow was taken at the Giants ballpark here probably about 5 years ago. And it's close to evening, so you can see it's, because it's directly opposite the sun was very low. And you can also see that you don't see almost all the colors of the rainbow because it's mostly red light you're seeing, so it's all tinged. Hang on just a second here. So as we all know, most people, and most everybody knows this already, but rainbow characteristics, light. I don't know if you remember from school, but Roy G. Biv are your colors: red, orange, yellow, green, blue, indigo, whatever that is. It must be some kind of blue, and violet. And but if the conditions are all right, when you look at a rainbow and you get your primary bowl, you get a lighter area underneath it. You get a darker area right in here, and then you have a secondary bow, which where your colors are reversed. So I went online and I tried to find out some easy explanations of what's happening, and that's kind of stuff you get. So I actually brought a prop with me, but I'm going to wait till I go through the whole slideshow here, and then I'll show you what's actually happening with raindrops. And so we'll move on to, and rainbows are individual for, for every person sees their own rainbow. The person next to you sees a different rainbow, even though you're looking at the same direction. So you have your own personal rainbow you're looking at. And actually, technically, your right eye sees a different rainbow than your left eye sees, but your brain puts them both together. And so anyway, I took this from a few years ago from my backyard. And what I noticed was that the hills off in the distance, you can see the rainbow coming down right next to that tree. And I'm thinking, well, if I'm controlling where that rainbow's at, if I walk, and I figured out how tall a tree is there, if I walk a certain distance in my backyard to the right, I probably can drag that rainbow over to come right over the top of the tree. And there it is. So a rainbow is always, they can only be so big. It's a 42 degree from your subsolar point, which is directly opposite the sun and the sky. And so when you get your biggest, tallest rainbows, it's going to be there in the morning, right when the sun comes up, or right when the sun's going down. You have a 42 degree height of that rainbow. And sometimes you see shortened rainbows. This one here I took from my backyard in Clayton. And it was in the evening, and you can see it's mostly on the reddish side. And rainbows, as I said, they're biggest in the evening, but during the height of when the sun's up high, then your rainbow is going to be, since you're looking directly opposite the sun, the height of the rainbow is going to be very low until you get up to noontime. You're not going to see any rainbow. And then I did not take this, by the way. If you happen to be around a lake when it's raining and there's rainbows, you can see multiples going every which way. So this one here, this is actually a power plant over in Pittsburgh where I retired from. I worked there for like 38 years. And I don't know, probably about 10 years ago or so, I was at work and it was raining. I just got to work in the morning, and it was about 9 o'clock, and I see this rainbow. And I happened to be, we had a little golf cart, so we drove around the plant to get to different places. And I jumped on the golf cart, drove past my truck, grabbed my camera, and I started driving around. And I found a good spot because I could make that rainbow go wherever I wanted to, depending on where I was. So I took that shot, and then of course, showed it to the plant managers, and they went ape over it. And then they blew up the picture, and it was hanging in the lobby for the plant until the plant's closed down now, but it hung there for about 10 years. So if you ever want to know anything about atmospheric optics, there's a website you can go to called Atmospheric Optics. And they talk about all the various different halos, rainbows, different diffraction effects. And they'll show you when you see a halo around the sun, around the moon, or you see a rainbow in the sky where it doesn't seem like it belongs there. It's because what you're looking at is you're looking at ice crystals causing that. And ice crystals come in all kinds of various different shapes and forms. And so just look at them as being a prism in a different shape. So depending on the clouds that you have, the ice crystals, you can't have too thick of a cloud. You won't see any halos. If you have too thin, there's not enough there to see them. The conditions have to be just kind of right. This I took from my backyard. That's Mount Diablo at the very bottom there. But this is certain ice crystals will give you a 22-degree halo. And there's what's called a perihelic circle up there. And it's hard to kind of see in this picture, but in the next picture. Okay, you see this real faint line going right through the sun. And there's an entire circle. And I remember seeing almost the entire circle when this happened. And it's just the types of shapes of ice crystals that you have in above you there. So this is called a Circum Horizontal Arc. And it's just it's from the ice crystals that make up the cloud. And there's the same crystals all over that cloud, except you got to be at the right angle with the sun to see those various different colors. So that's what's happening there. This is called a circumzenithal arc. And this is not my picture, but I have seen a couple of them in the past. And what's strange about them is it looks like a rainbow, but it's centered on your zenith straight up. And you only get part of it, like it's a smiling face at you. So if you're around and you start seeing some halos in the sky, look straight up. You might see one of these. Has anybody seen one of these? Yeah, a couple of them. They're kind of rare. And most everybody's seen a sundog. And then up at the top here, this is what's called the upper tangent arc. There's various different arcs, and then here. And there's also a 44-degree halo that's way out that looks like a rainbow. All this stuff is up there, and a lot of people never look up and never see this. So this is a sun pillar. This is a result of, it's ice crystals in the air, but they're the ones that are flat, just like little flat mirrors. So all the ones up above the sun, you just see this pillar of light. And you can also see, sometimes you can see, and usually places up north that are very cold, you can see street lights, city lights. I'll have these pillars coming up from them at night. This is, to pull this off the internet. But people sometimes see these things, like, especially if they go skiing in some place it's really super cold. And you see this, the sky is actually blue behind it, but all those crystals are very close to the observer. So all that snow flying all over the place throws all these crystals up there, and then you get all the various different combinations. Okay, now we're going to go into what's called the crepuscular rays. These are basically, they're not really rays, they're shadows from clouds that are, you normally would see these at sunset. And so you see these linear features. And so anytime you get a sunset with a lot of clouds, you can see, they all seem to, it's a perspective. They emanate from the sun, seems to, and then they spread out and they'll go right over your head. This one is kind of a strange one. I guess it qualifies as crepuscular rays. I was taking a walk on Mount Diablo one day, and the sun had just kind of set behind this hill, and there was a little bit of fog there. And so what you're seeing is the shadows of the trees extending over into the fog. But it still qualifies as crepuscular rays, I guess. So I had to really process it and do a lot of contrast to get that to pop out, but there it is. So these are what's called antiprepuscular rays, and they're the shadows that are basically extending right over your head and all the way to the eastern horizon. And I saw this a couple of months ago at sunset. So I'm actually looking east. And you can see those dark streaks going right over my head, kind of converging into the east. So this is called a glory, and this is another picture I pulled off the internet. But in days when there's fog out and the sun's starting to shine through, sometimes if you look at your shadow, you can see a little, rainbow around your head. And it's all this refraction with the raindrops.
Say, Mike, you can also see that from an airplane.
Oh, yeah, I was going to point out. Yeah, that's where most people see it, is when you're flying from a plane, you're coming for landing, you look out the window and you see the shadow of the airplane and see the same effect. And then, of course, there's a green flash. Anybody seen the green flash in here? Okay. Well, that's a whole different talk altogether, but that's all due to refraction and pretty interesting effect. What else I got here? Oh, if you ever want a picture with a halo around your head, I think it's the first selfie I ever took. But actually, you can, if you see these halos, you're always trying to figure out you need something in the way, just do a selfie with your, So now I'm going to stop screen sharing. Okay. Now I'm going to get out my talk about rainbows a minute.
Oh, good.
And I'll do it in front of the camera here so the Zoom landers can see it. So, contrary to popular belief, raindrops are not shaped like raindrops or teardrops, or they're actually spherical. Because if they weren't spherical, you wouldn't see any rainbows, for one thing. So here's a raindrop. And what happens is, remember when I showed you the picture, you had the primary arc, and inside you had a brighter area, and then you had a dark area, and then you had the reversed rays. What's happening is, when you were looking at, I don't know if you can see it. I don't know if you can see it. Anyway, there's a rainbow inscribed on here. So every raindrop projects a circular rainbow. Okay. So if the sun is directly behind you and you're looking at the raindrop, what you're seeing is basically, this is acting like a convex mirror. You're seeing a little image of the sun popping back at you. That's what that bright area is. Okay, then as you move out, this raindrop is over here. This, say the red color is projecting to Marnie over there. The reflection sun's pointing this way. And then over here, they're looking at, they might see red, but actually remember, your raindrops are always way up here somewhere. And there's always a bazillion of them, and they're always moving all the time. And so that's why everybody's not seeing the same raindrops all the time. So, and then what happens here, and then there's a dark area that's outside of the primary. That's because the light bounces around in here, comes back out as the primary rainbow, then it bounces around some more, it comes out reversed as a secondary rainbow. But the area in between is not projecting anything out of it. So when you're looking at that, you're just seeing dark. You're not seeing anything. That's what that dark area is. And then the secondary, because it's so little light that it's bouncing around several times before it comes out, is always much fainter. So that's basically it. What? Oh, 3? Yeah, there's actually, you go on that one website, they have several different ones. They have rainbows that are actually what they call twinned, and or they have superluminaries, which they have extra arcs in them. And that's all the theories are, because some of the raindrops are a little bit different sizes. So, yeah, Kent.
I once was flying between Northern and Southern California. I don't know what height we were at, tens of thousands of feet, I guess. And we had just the right conditions. The sun was near zenith and there was rain below the plane. And I saw a 360-degree circle rainbow.
Yeah. Yeah, you,
Yeah.
because, these things are three-dimensional circular. Yeah.
And the primary is result of a single reflection
Uh-huh.
on the backside of the raindrop.
Mhm.
Secondary is a triple reflection.
Yeah. Yeah.
Bounces off the back, bounces off the front, comes
Yeah.
out.
That's why it's so faint.
Yeah.
There's very little light left. Okay. Thank you very much.
All right. So tonight's talk is entitled Cephieds, Supernovae, and the Cosmic Background, Microwave Background. I knew I was going to screw that up. I'm pleased to introduce Dr. Lloyd Knox to our meeting tonight. Professor Knox was educated at the University of Virginia, obtaining a BS in physics in 1990, and at the University of Chicago, obtaining his PhD in physics in 1995. After a postdoctoral appointment at the Canadian Institute for Theoretical Astrophysics from 1995 to 1998, and the University of Chicago from 98 to 2000, he joined the faculty of the Department of Physics at the University of California, Davis, where he remains to this day. In 2012, he was elected as a Fellow of the American Physical Society with a citation that reads, "For motivating major observations, WMAP and Planck, and developing widely used data analysis tool, providing insightful interpretations of data and calculating the impact of astrophysical processes on the microwave sky." An author of hundreds of papers in his field, he enjoys sharing his enthusiasm for physics and cosmology with a wide range of audiences, including third grade classrooms, students at UC Davis, and astronomical societies. And so I'll ad lib here a little bit, and hopefully we're one of those astronomical societies that you like to visit.
Absolutely.
Please welcome Dr. Knox.
Well, thank you for that introduction and that warm welcome. So it's great to be in a room with people curious enough about astronomy that you have a club and you regularly come here. And, I went into my field because of, similar reasons, driven by my curiosity, but it also is often a job. I've got to write this letter of recommendation. I got to fill out this form. I got to write this grant proposal. And I can sometimes, not be in touch with that natural curiosity. And coming to talk with a group like this always just renews that energy in me. So thank you all very much for this opportunity. So I'm going to talk about, as Dave said, Cephieds, supernovae, and the cosmic microwave background. And before I get right into that, I'm going to give a little historical context and go back to thinking about the solar system as was understood in about 1845. So now in 1845, we didn't know about Neptune and we didn't know about Pluto, but we did know about Uranus and all these other planets here. And we also had this amazingly successful theory of gravity, Newton's universal gravitation, and did a wonderful job of explaining the phenomena of the motions of these bodies. And let's see, I need to adjust something in my viewing here so I can get rid of some stuff that's in my way. No. Oh, here we go. Okay. And in the around 1845, two people independently, Urbain Le Verrier in France and John Couch Adams in England, worked out how Uranus should be moving, given the dominant pole of the sun on Uranus, but also the perturbations that came from the other planets. And he found that they found that Uranus's motion couldn't be explained by the known planets and Newton's theory of gravitation. And they both boldly came up with the same solution, which is that there's some unseen planet causing this. And they were even able to say, if a planet had this orbit, it would do the trick. And so would some astronomer please go observe and find a planet? John Couch Adams anyway, had real trouble getting somebody in England to pay attention to him and follow up on that. Urbain Le Verrier had better luck and went to Johann Gall. Why is this not advancing? Oh, I need to, okay. And the next night, Johann Gall discovered Neptune. And if you look at this picture of John Couch Adams, this is him, I think, much older than when he was trying to do this, but it also looks like he's kind of saying, next time I tell you there's a planet you can discover, how about you go look? So that's a tremendous accomplishment of Newtonian theory, right? Predicting where a planet's going to be and having that discovered. Now, Le Verrier, about 10 years later, was sitting in a cafe, enjoying his fame at having, basically discovered Neptune, when the thought occurred to him, well, yeah, but what have I done lately? And so he turned his attention to Mercury and calculating the motion of Mercury. And Mercury does this interesting thing. So to a first approximation, it rotates on an ellipse, as you'd expect from Newton's law of gravitation, and just having one dominant force pulling on you, then the orbit would be an ellipse. But because of, mainly due to perturbations from other planets, that ellipse doesn't stay in the same orientation. It slowly rotates around. And we call that a precession of the ellipse, or a precession of perihelion, that location of closest approach to the sun. And he calculated, I mean, they didn't have computers back then. This is amazing, right? This is really hard work. I'm just impressed that they could do this. Calculate what the other planets pulling on Mercury would do to the motion, and calculated the rate of this precession that should occur, and got very close to the answer that was consistent with observations. The discrepancy was tiny, 1/10,000th of a degree per year, right? So 360 degrees would be all the way around. 1/10,000th of a degree per year is how he was off in the rate of that precession. I would have said, all right, job well done, Lloyd. You got it. Let's go on. What else should I do? But he actually had also done enough control of the errors in his calculation to know that this was not, that there was something up here. This discrepancy was interesting. So I want to abstract this a little bit to tell you what was going on. So there was there were kind of two ways of getting at the rate of perihelion precession of Mercury. There was the less model dependent way of observing Mercury's position in the sky over time and working it out from that. And then there's a more model dependent way where you're taking this very successful theory. I mean, it had been used to discover a planet, among other things, plus solar system observations, right? You need to know where those other planets are that are perturbing Mercury around, and use that to predict the rate of perihelion precession of Mercury. And these are different rates. And that motion of Mercury wasn't understood until Einstein stumbled upon a solution in 1915. So I'm gonna do an experiment here of actually pausing several times through the talk to ask for questions and discussion before going on. So this is my first pause here. I didn't realize that would mean Dave would have to run the mic around.
That's all right. Mine. As long as everybody flags me down so I can bring it to them. No questions? There's one.
So when Einstein was working out the general theory, did he have this problem in mind, or did it fall out of the general theory?
Yeah, excellent question. Thank you for that. He was trying to solve problems, right, in getting a unified understanding of electromagnetism. So some synthesis of experiments with electricity and magnets and gravitation. And those were the things driving his work towards a new theory of gravity in space and time. And so he was not trying to solve this problem of Mercury. But it was you can imagine how excited he was when he was actually able to work out, once he had his new theory and was able to work out the prediction, and he found this solves this problem that's been outstanding for over 40 years.
Yeah, I'll get it in a second. Yeah. I go pull it up here first. And that question is, always heard the three-body gravity calculations are difficult. How do they solve multi-planet gravity effects?
Yeah, right. So this is in a regime. So yes, the general three-body problem is difficult, not amenable to analytic calculation. This is in a regime where these other bodies are causing very small corrections, and so it's a different regime of the calculation, and it's much harder than the general three-body problem. Okay, thank you for those questions. Yeah.
Oh, we have one more. I'm sorry. Didn't see her. You have to raise your hand a little farther up.
Okay, so the precession for Mercury that you were talking about does that happen with like every planet, or is it just Mercury?
It happens to some degree with every planet. It's particularly pronounced for Mercury. So the reason I went through that historical context is that the main subject of what I want to talk about today can also be framed in the same way, where we have observations of Cephieds and supernovae that can lead to a measurement of the rate of expansion of space today that's not dependent on assuming a cosmological model. So this is a less model dependent path. And then we have a more model dependent path towards predicting the rate of expansion of space today. We have a very successful theory, successful enough that we call it our standard cosmological model, sometimes also called lambda CDM. And then our observations here are observations of the cosmic microwave background. So I'll be explaining more about these things, but this is the kind of framework for the conflict, the discrepancy. And the reason it's interesting is the possibility that what reconciles these is something wrong with this very successful theory, right? So it's really that the perihelion precession of Mercury was happening because in order to understand that properly, it required a transformation in our understanding of space and time. A really fascinating one. And anyway, the great hope and dream is that maybe we're on the verge of something like that. Although it could also be, and probably is, something more prosaic. So what is the expansion of space? First of all, the units that we use to measurement, and the symbol for the expansion of space today is H naught. So H is for Edwin Hubble. This is the Hubble rate. And with the 0 subscript, that means for today. That's the Hubble constant. And it's constant in space. And it's one way of expressing its units is kilometers per second per megaparsec. And I'm giving credit to Leonard Balkenhol for making this figure, but you might wonder why I'm crediting. The figure is going to get more interesting. So this expansion is a creation of space, and one way of thinking about it is at least in this idealized notion of a completely homogeneous universe. Right now, there's in every megaparsec, which is about 3 million light years, there's about 70 kilometers being created every second. And this was, the reason we think about this way is because of Einstein's theory, that we can think about space being created. Here's the, just to get to the bottom line first, our most precise measurement right, I can use that. Our most precise measurement of the expansion rate today comes from using Cephieds and supernovae, and comes in up here. And then we have this very model dependent measurement using observation of the cosmic microwave background and coming out here. And these are error bars. So this is expressing, uncertainty about the measurement. This is saying that with 68% probability, it's in this range, and 95% would be about twice that range. And these are really discrepant. So this is a highly statistically significant difference. And the question is why? And we don't know yet. So what I'm going to talk about is first the expansion of space. I mean, there's this discrepancy in the expansion of space, but people don't usually understand, even people interested in astronomy might not fully grasp how radical the notion is of the expansion of space. So I want to talk about that first and get that across before talking about Cephieds and supernovae, and then at least saying something about the microwave background and inferring it from that. So, okay, who's heard of this equation? All right. Yes. So this is of course the most famous physics equation on the planet. This was Einstein's 1905 smash hit success. Not as many people are familiar with this one. It just, I don't know why, some things catch on, some things don't. And I'm not going to be teaching you about Einstein field equations except very coarsely. On the left-hand side are things that describe space, and on the right-hand side is matter. And the takeaway here, right, is matter affects properties of space. And let me just make that a little more concrete. So you can construct a circle. You could take some string of radius r, right? Find the set of points that are equidistant from the center, and then you could measure the circumference, and you could see what you get. And if the geometry of the space is Euclidean, you get the result you learned in school. Now, if you have some mass in the middle, the circumference is actually going to be less than 2 pi r due to the mass at the center. And this is the consequence of Einstein's theory, or at least, well, this is the consequence of the way nature is. We understand it through Einstein's theory. And this is a real effect. The correction to the circumference of the moon's orbit is about 10 centimeters. So this is also why, Euclidean geometry is a really good approximation and why you were taught it in school. Now, to help you visualize a different geometry, I'm going to rely on, I forgot about sharing sound. I forgot I had this. And so I am just going to do this without the sound. We'll miss the drama. Okay, so here's this object, and we're interested in the circumference of the object and how that compares to the volume inside. So this is a space that's very different from our Euclidean intuition. And so this is occurring to her, and she's going to go investigate. I totally forgot I had something that had sound. Okay, come on, you guys, get on with it. So she's measuring the circumference, right? And she's comparing it to the radius, and it just doesn't add up. So that's a non-Euclidean space, and space is non-Euclidean. It's just that it's a very good approximation to Euclidean around here. And I happen to have a TARDIS with me right here. And what I want you to imagine is that there's about 5 liters of space inside this. Everybody imagining that if I open this door here, you might see, so you had some help, right, from that video. So imagine there's 5 liters of space inside here. Okay. Now imagine that the space inside here is actually increasing over time. So now it's 6 liters. Now it's 7 liters. And it's just getting, that's the creation of new space. That's the expansion of space. What I'm trying to overcome is that you usually think of the expansion of space as stuff flowing out into existing space. That's not what we're talking about here. So there could be new space being created over time. There could be an expanding universe inside this thing. And from the outside, it doesn't have to be increasing. So that's the radical departure, radical change to our notions of what space can do that Einstein's theory introduced us to. And yes, absolutely.
Can the discrepancy between the two ways of measuring the expansion of space be reconciled by the inflationary model? In other words, a more rapid inflation?
It actually can, but that's not such a satisfying answer unless I say more. And it's let me get a, why don't we,
Okay,
maybe you
we'll
can
get
want me to come
there.
back to
Right,
that
right,
later
okay.
when we've said more about this.
Anybody else? Question? No? No? Okay. Oh, there's a chat. All right, Colin. Oh, God. Anybody see that?
Okay, so let's talk about measuring the expansion of space with Cephieds and supernovae. So the expansion rate is determined, I put directly in quotes because there is certainly some theory involved in interpreting the measurements that are done here. But the fundamental measurements are one of distances and redshifts. And you probably all, I mean, you're amateur, you're here at an astronomical society. I'm sure you know what redshift is, but let me just review it, right? 1 plus z is related to, it is the wavelength of light observed divided by the wavelength of light emitted. So if light gets stretched out, z is positive. We call that a redshift, right? If this is blue light when emitted and it's stretched out to red light, right? It's been shifted to the red. And I'll come back to this. Whoops, got to use this again. I'll come back to this equation, but if we measure, I'm talking about measuring distances and redshifts. So if we can measure distances and we can measure redshifts, and c is the speed of light, they're related to the expansion rate in this way. I'll come back to that. But first, let's just talk about redshifts. And since I thought that this would be a good occasion in talking about redshift to show an image and a spectrum from the James Webb Space Telescope. So here's part of an image, and in this little dot here is light from a galaxy that light has been traveling to us for 13.1 billion years. And down here is a spectrum. So this is let me zoom in on the spectrum. So this is the wavelength of the light, and this graph is showing the intensity of light as a function of its wavelength. So this is like the rainbow that we were seeing earlier, not as pretty. And the astronomers looking at this spectrum have managed to figure out what atomic transitions correspond to which of these emission lines. This light being emitted from hot gas in this galaxy. And the way the units here are thousands of nanometers. If we look at an emission line spectrum of hydrogen, so if you heat up hydrogen, if you get hydrogen gas really hot, then it will glow, but it won't glow the whole rainbow. It'll glow, right, these discrete colors, these discrete wavelengths. this is H alpha. This is which is anyway the name to a particular electronic transition in hydrogen causing this red light here. This is H beta which has a wavelength of 486.1 nanometers. The astronomers tell me that this is H beta here, and it's seen with a wavelength of 4.6 thousand nanometers. So if we take that wavelength observed, 4,610 nanometers, if this is H beta, it was emitted with 486 nanometers, right? These are the same atoms. This is our assumption of the universality of physics. These are the same hydrogen atoms in this galaxy as we have here on Earth. So when that light left at a wavelength of 486 nanometers, and it's been stretched out to 4,610 nanometers, that's a factor of 9.5. So what does that mean Z is? So, oh, wait, okay. I also wanted to run through another one. So here's H gamma, 434 nanometers. This is H gamma with a wavelength of, observed at a wavelength of about 4,120 nanometers. And again, we have the same ratio, right? So that's a good consistency check. This light has all been stretched out by the same amount. And so the wavelengths of light arriving at JWST from this object are 9.5 times longer than when they were emitted. That was 1 plus Z equals that ratio of wavelengths, right? So Z, the redshift is 8.5. Okay, let me, unless there's a burning question right now, I'm gonna keep going. Okay, so, but why? What happened? Why did the wavelength increase? So here's a little cartoon of the expansion of space happening over time. So this is some two-dimensional model of the universe seen expanding here over time. Of course, the universe is three-dimensional. So this is just a two-dimensional analog. And as the universe is expanding, the wavelength of light traveling through the universe is stretching up with that expansion. So when light was sent from, oops, I'm supposed to be using this. When light was sent from this object to this object, and it initially had some small wavelength. It's getting stretched up as it travels. It's getting stretched out by that expansion. And that's the impact, and it's actually the ratio, the amount it expands actually tells you how much the universe has expanded since light left the object. It's kind of amazing that we have this opportunity to make an observation, and pretty directly that connects with how much the universe has expanded since light left that object. So not only is that ratio of wavelengths tell us that the universe has expanded by a factor of 9.5 since light left that object until it arrived at JWST. So that's redshift and how it connects to the expansion. And now we should talk about distance. And so so how many are familiar with the classical distance ladder? Okay, I expected there'd be some familiarity with that. So it used to be more complicated than this, right? But it's actually simplified a lot because we can do parallax to a lot of Cephieds now. So the step one is using geometric parallax to determine distances to Cephieds. Then Cephieds have this relationship between their period and luminosity. This allows us to calibrate. Actually getting a distance to some Cephieds allows us to measure the flux coming to us and actually tell how luminous the Cephieds are, how much energy they're putting out. So then we have this standard candle where if you measure the period of a Cepheid, you can determine its luminosity. And then if you measure how bright it is, you can determine the distance. And Cephieds are bright enough that we can use this out to galaxies such as M101, where there are supernovae, and use that to calibrate some aspects of supernovae, and then use the supernovae to go to even further distances too far for where you see Cephieds. Here's an image, which may be a little bit hard to, anyway, I'll blow it up in a second, but here's, I want to zoom in on this part first here. This kind of tells the whole story of using Cephieds to calibrate supernovae. And is starting off with using parallax, right? So the Earth moving around the sun and getting a different vantage point on a nearby star. So, right, if you hold your thumb out and switch between your two eyes, you see your thumb shift relative to further objects, right? You hold your thumb closer, it'll shift even more. So you can figure out. It's one of the things I have my students in a cosmology class do, is one of our few lab activities, because it's a theoretical course. We go outside and they're all going like this. We did this in the winter and somebody walking by went. And we measure the lengths of our arms, you know, so. And here, you know, you can see how one looks at how the apparent position of this nearby star shifts relative to background ones. Right here, it's lining up with this. Later in time, it's lining up with stuff over here, and use that to infer the distance. These parallax shifts are small and hard to measure. And a new technique using the Wide Field Planetary Camera 3 on the Hubble Space Telescope was used to push that limit out quite dramatically, a lot further, allowing for measurement of a lot more Cepheids. This is really helpful to increasing the precision with which these distances could be measured. Right, this relationship between period and luminosity was discovered by Henrietta Levitt, who was hired as a computer, right? Someone to just act as an automaton to make, you know, it's difficult work, and one had done with care, but she was more than that, and she noticed this relationship between period and luminosity in Cepheid variable stars, and also realized how important this would be in astronomy, and wrote that you know, it'd be great if we could get parallax to Cepheids and calibrate this and use these as standard candles in astronomy, and that has come to pass. It's been critical to the precision measurements of the Hubble constant. So those Cepheids are also visible in some nearby galaxies. They're not all clumped just to one side of the Milky Way, right? They're spread all around. Nearby galaxies where there are supernova explosions that have been recorded by the Hubble Space Telescope. And then that allows one to calibrate the luminosity of supernova explosions, which are also can act as standard candles, and those can be used. Then those are significantly brighter than Cepheids and can be used to reach out to even larger distances, which is a quite helpful thing for measuring the Hubble constant. Now, why you want to get out to far enough distances, because the universe is not completely homogeneous, right? A completely homogeneous universe would have this uniform expansion. Would have the drawback that, of course, we wouldn't be here. We need departures from complete homogeneity in order to have stars and human beings. But those departures from homogeneity create gravitational poles that create other sources of redshift that we call peculiar velocities, right? So Andromeda and us are falling in toward each other, as I'm sure you know, and so light from Andromeda is blue shifted towards us. That's not because it has a negative distance. That's another, you know, source of a shift of the wavelength of the light. And if you get out to far enough distances, this effects of expansion will dominate over these other contributions to the redshift. So that's why you want to get out to use the supernovae to get out into what we call the Hubble flow, where the redshift is dominated by the expansion of the universe. So here's a plot of the data points on here are actually, you know, these are from measurements of hundreds of supernovae and just and using them to infer distance and just kind of binning a bunch of supernovae together here to get a small error bar on one measurement. And that's what's happening to create these pretty precise error bars of something called the Pantheon supernova collection. And down here we have measurements of the redshift of the supernovae times the speed of light. This is z equals 0.1 out here. So this is definitely in this is not in the same regime we started with, right? Where z equals 8.5. These are much smaller redshifts. And these are small enough redshifts that we expect this linear relationship between distance and this c times z. And then here's right, the Hubble constant is basically depends on the slope of this line. And here are different predictions for different Hubble constants, right? Here's the Hubble constant of 50 kilometers per second per megaparsec. Here's one for 150, and then here's one of 70. This might be a good time to pause for a question since we didn't. Yeah. Yes, we do. Want me to run it over there?
Oh, that's all right. Whoever's, oh, there you go.
All right, thank you. Going back to non-Euclidean geometry, you talked about the effect of gravitational mass on the moon's orbit, but my understanding of the universe is that it is a flat with a Euclidean geometry. Is that the difference between the large scale and small scale?
Yes, exactly. So on average, if you coarse grain a large enough part of the universe, the curvature, the spatial curvature is very near zero. And you know, locally we have departures from that. I mean, certainly like, and then we have huge departures from that, you know, in the vicinity of a black hole. But exactly right. It's a matter of scale. That on large enough scales, if you're looking at how light propagates over very large distances, and then the curvature, as we found out from measurements, turns out to be quite small. And this expansion of space, though, that is happening, is a there's also something called the curvature of space-time, and that is not a flat space-time, but that's not the kind of curvature I've talked about. Anyway, I shouldn't have gone there, perhaps. So, you know, there's a lot that goes into these measurements that in the time I have here, you know, I did not go into at all. But if I was going to say anything at all about the cosmic microwave background and have time for questions, that's how it is. By the way, these pictures here, does anybody know why I would have chosen this picture for Cephieds? Polaris, right. So Polaris is a Cepheid. And then this is one of the two possible mechanisms for creating a type 1a supernova is the accretion of a white dwarf with a companion that it's accreting gas from. And then eventually it accretes enough gas that the electron degeneracy pressure that's holding up the white dwarf can no longer keep it supported against gravity, and it collapses, and there's a thermonuclear explosion that happens with that collapsing.
There was a chat question which had, as space expands, are the interacting forces between particles getting weaker?
As space expands, well, if the particles are getting further apart from each other, yes, but not everything's expanding. I mean, our bodies aren't expanding. Soon after I got, oh, well, okay. I should actually look at the data sometimes. Soon after I got hired at UC Davis, my department chair came into my office, closed the door, and asked me, "So is the Earth expanding too?" And again, right, this uniformly expanding universe is it's like the most spherical cow approximation of all time. It's if the universe had no features to it, if it were completely uniform, then we'd have this uniform expansion. The universe is actually much more complicated than that. So there's a lot more mass in our galaxy than just right outside our galaxy, and so the space is different, and it's not expanding. Yeah.
Here you go.
You've referred to the standard candle, Cepheid variables and the type 1 supernova. How do we know they're standard? How similar in energy can these phenomenon be? What we're saying is that every Cepheid variable is a standard candle, has a standard luminosity. Every type 1A supernova has exactly the same amount of energy released, and so therefore we can say it's a standard amount of energy. I mean, that doesn't make sense.
Yeah, no, it's a great question. Let me just take the supernovae. So in fact, the supernovae definitely aren't standard candles. There are differences in how these explosions proceed. I'm not an expert on the supernova physics, but there's differences on how these explosions proceed, and some get to a higher peak luminosity than others. So there's some spread in that peak luminosity. A lot of this is empirical, and one of the there's been a relation discovered that so some supernovae are near enough by we know their distances, right, from other methods. Of course, you just questioned the Cephieds, but allow me the Cephieds for a moment. And so you can study nearby supernovae and look for diversity of results. So certainly there is a significant difference in peak luminosity, but it's correlated with the width of the time it takes to actually go back down in brightness. And so there's a property you can also measure that's correlated with peak luminosity, and you can correct for it. And so people refer to these as standardizable candles. But the question still remains, is there something different? The really worrisome thing is there something different about your population of supernovae in the nearby galaxies, the ones that you calibrated with supernovae? Is there something different between those and the ones out in the Hubble flow, and that are then used to determine the expansion rate? And that could bias, if there was such a difference in this nearby population and from population further away, that could definitely bias the results. And this is exactly the territory. This is exactly one thing that the supernova community, really argues about, right? And it's why there's a significant effort gone into nearby supernovae where we can get distances to them and search for the diversity of these events and try to categorize them and control these systematics. Now there is also, I said this is entirely empirical, there is also a theoretical understanding of why there is this relationship between peak luminosity and how long it takes for the light curve to play out. But it's largely empirical, and it's a source of concern. And similar questions arise with Cephieds, and there's effects. And anyway, maybe we could talk more about that later. But you're exactly right, and this is one reason that so I come from a community that pays a lot more attention to things that are easier to understand. The cosmic microwave, to me, the cosmic microwave background is a much easier thing you can calculate what's going on in it from first principles. It's much more amenable to theoretical calculation. Supernovae and Cephieds are very complicated. And so people like me view this with a lot of skepticism and think, well, they've screwed up something with the astrophysics. But then I talked to Adam Rees, and I always come away thinking, wow, they've really thought of everything. Then I talked to Wendy Friedman, and she has, anyway, I get a different perspective, who also works with Cephieds and supernovae. So my main takeaway is that from all this is that I'm an outsider. The experts in this area are not all on the same page. This is to me, this is the more likely thing to shift. But if Adam Rees were here, he would convince you otherwise. We really don't know. We don't know how this resolves.
Read that message there.
What's the current status of the theory that perhaps the speed of light is not quite a constant, and does that explain the discrepancy? So I guess the current status is that theory is not getting a lot of attention, and could it explain the discrepancy? I'm not sure. I'm not sure. I'd have to think more than I want to think right now. Because you all would be waiting while I'm thinking. And then my answer might still be the same. I'm not sure.
I don't think Einstein would be happy either.
This may be, I'm not sure what the gentleman means, but this might be a thought, is that light speed is constant, but that would mean instantaneous. That if you're talking about if you're talking about non-inertial reference frame, he might perhaps be thinking of the idea of the apparent velocity of light would vary, not instantaneous speed, but just passage through a gravitational field. There's some effect. I can't remember what it is, but it's some
gravitational lensing.
Yeah, but there's some counterintuitive thing where that longer distance is actually the apparent. There's actually the shorter actual displacement of it's just that the curvature of space and time causes a curved space to actually be the natural mean free path. I don't know. You're the physicist, so you would know more about it, but
there has been a theory. You brought up inflation, and this is actually an alternative idea for inflation, to have a variable speed of light in the early universe.
Okay.
I think this is what they're talking about.
Oh, I see. So there's an actual. Okay, never mind. Yeah. Yeah, another theory.
So I want to talk. I've mentioned the cosmic microwave background many times now, but I haven't really said what it is. And so let me say a bit about that. So this is a cartoon of the thermal history of the universe, right? So the universe is expanding, and as it's doing that, it's cooling. So the expansion of the universe actually, the kinetic energy of all particles decreases due to the expansion. So we know that that's happening with these particles of light called photons, right? As their kinetic energy is decreasing, that corresponds to their wavelength stretching out. This is happening to all particles in an expanding universe. The expansion, the momenta of all particles slows down with the expansion. So everything cools over time. And so conversely, right, earlier, the universe was much hotter, and it used to be so hot that it was an ionized plasma, like the interior of the sun. That's okay. Oh, you got that? Wow. Okay. And so we have this plasma, which means that the collisions between particles are so energetic that the electrons couldn't stay bound to nuclei. If it was briefly bound to a nucleus, a collision would happen to knock the electron out. So there's all these free electrons floating around here, and light scatters very readily off of a free electron. So this was not only a plasma, it was opaque. So light couldn't travel through this until the universe cooled enough that electrons could bind to nuclei and stay bound. Then you had a neutral gas, just like the gas in this room, and light could travel freely across the whole observable universe. So that's an important transition that happened. And we can see light that's been traveling since that time. This is our past light cone. So this is here and now, and as we're going out in this diagram, we're going back in time as well as out in space. Here's the time of that transition where this light, this thermal light, last scattered before traveling off in a gazillion different directions. Some of it traveling right toward us, right? And that's the light we can see. And if we look at the sky in millimeter wavelengths. And so we can image this part of the universe by looking at it in millimeter wavelengths. So just to orient you, here's the optical sky at night, wavelength of around 10 to the minus 3 millimeters, around a micron. And here's the wavelength. If you instead had eyes that were sensitive to wavelengths around 2 millimeters, the microwave wavelengths, you'd see something like this. The color here indicates the brightness of the light. This doesn't look too informative, right? But this reflects how uniform the early universe used to be. There were, though, small departures from complete homogeneity at that time, and departures that slowly grew under the action of gravity to be the diversity of structures we see in the universe today. And if we look at this more sensitively, if we can increase the contrast sufficiently, then we can start to see those departures. And these are brightness fluctuations at the 1 part in 100,000 to 1 part in 10,000 level. These are very small variations in brightness. But my experimentalist colleagues have been able to make instruments that have been able to image this. Here's using a different color scale. If you had this great contrast, what your eyes would see in the sky at millimeter wavelengths. And there's a lot more I could say about this system. I'm just going to tell you, give you an analogy with the solar system, right, which we started off talking about in the beginning. So the solar system is this remarkable gift of nature, at least to those who are interested in trying to understand nature. It's an unusually simple and regular natural system. In fact, I mean, the ancient astronomers had this view of the cosmos where they referred to the sublunar realm as the corruptible realm. Everything's here too complicated to actually understand with mathematics or laws. But the heavens, right, above the moon was regular, and they called it incorruptible, filled with ether. And that's because it was just this simple and regular natural system. And it was, of course, observable. You know, you can see the motions of the planets. Of course, you all have. Once we had Newton's theory, it's calculable. Well, it was calculable with earlier theories too, right? There was Ptolemy's theory, and you could make calculations with that and compare with observations. It's phenomenologically rich. You don't just have planets moving across the sky in straight lines at uniform speed. You have interesting things like retrograde motion. That's a really important clue to start to figure out what's actually going on. And of course, we had this highly successful theory, Newton's theory, you know, for example, the discovery of Neptune. And likewise, the primordial plasma. It's this unusually simple natural system. I mean, most natural things are too hard for us to calculate from first principles. It's why we do experiments, right? We do physics experiments where we set up the conditions in some idealized way so that we eliminate all the complications and we can actually try to predict what's going to happen. and then can compare with what does happen. But here we have a natural system that's unusually simple. It's simple because those departures from complete uniformity are so small that we can use what we call linear perturbation theory. We can take the equations of motion and ignore anything that goes as you know, a square or a cube of the departures from complete homogeneity. And we know how to do linear perturbation theory really well. We can calculate that very accurately. You know, supernova, much more complicated. This is child's play compared to figuring out how a supernova explodes. So it's calculable, it's observable. It's only observable thanks to the hard work of my colleagues, right? It's hard to observe this exactly because of the reason it's calculable. These are very small departures that we're talking about observing. And it's also phenomenologically rich in ways that maybe, you know, with that I was afraid I wouldn't have time to fully explain, but we can go into if we have time with questions. And there's this highly successful theory, lambda CDM. Again, I haven't had a chance to tell you about the ray successes of lambda CDM, but it's done a remarkable job of predicting the statistical properties of these microwaves as we've managed to make these maps with lower and lower noise and higher resolution. We've been able to test the predictions of this model, and it's been extraordinary seeing those results play out over the course of my career. So this is where we are. If you take the standard cosmological model, which has 6 parameters to fit, one of them is, you know, what's the value of the cosmological constant? What's the density of cold dark matter? What's the density of normal matter? And then a few others I could tell you about. If you take all this data and use that to fit these parameters, you can predict how rapidly the universe is expanding, and you can predict it quite precisely. And it's discrepant with the more direct model, cosmology model independent way of doing it. What's going on? Well, one thing to tell you about this lambda CDM model is that, well, lambda is what's responsible for most of the energy in the universe today. Dark matter is next, and then the stuff that the rest of science studies is a mere 4.6%. That's today. This is dynamic. This mix is changing as the universe expands. Back when the universe went through that transition from ionized plasma to neutral gas, the mix was quite different. Dark matter was 63%. Neutrinos made up 10% of the energy density. Photons made up 15%, and atoms 12%. And one of the possibilities, although I don't have time here to really explain how this would work, is that actually, before I go into that, the fact that this model is made up of this, and we don't understand what these are. Every time I've seen predictions from lambda CDM and we've worked out, oh, with these observations, we can test those predictions, I've thought, all right, you know, there's no way this model, this ridiculous model that is going to work. And it's just one every time. The most notable exception to that is this Hubble constant discrepancy. Anyway, maybe the dark sector is more complicated than this. Maybe there's an additional dark component that's important at early times, and that could potentially lead to this discrepancy. If that were present, it would change our interpretation of the CMB data and change our prediction of the expansion rate. So let me summarize here. So new space is being created continually. That's the expansion of space. The primordial plasma, like the solar system, is a great gift of nature to those of us trying to understand it. We have a standard cosmological model that is very successful empirically, and there's one major discrepancy, this having to do with measurements of the expansion rate today, and we don't know what the answer is. All right, thank you all very much.
We got any questions?
Yeah, sorry, it was the Shapiro effect was the thing I was thinking.
Ah,
before.
okay.
Sorry about that.
Sure.
But my real question is, and I don't know where that would have led, but my real question is, if that dark energy was there and it disappeared, would that violate the conservation of energy, or would it go somewhere, or how would that work?
So it depending on how quickly it disappeared. I mean, if one of the really strange things is that in some sense, in an expanding universe, energy actually isn't conserved. Like if you think about this photon that's traveling
Right.
from one place to another, it's losing energy. That energy is not actually going anywhere. There's a sense in which energy is actually not conserved in this expanding
Right,
space-time.
right.
Now, energy is locally conserved, and there's I mean, I guess if the equation of state, how pressure depends on energy density, were super stiff, so it actually was more like a tension. So it was a material that was hard to pull apart rather than one that resisted collapse. And it were tenser than anything we know, then it could disappear really quickly under expansion. But
Like the strong force?
yeah,
Sorry.
that's right. That, I mean, that does create this restoring force, which would be a tension.
Okay, well, thank you.
Yeah.
One for you.
Yeah, in your pie charts, so there was no dark energy in the early universe?
So if the dark energy is a cosmological constant, then what's happening is that as the universe expands, as the universe expands, the dark matter is, at least as we model it, is just these non-relativistic particles. Their energy is dominated by their rest mass energy. So they have some amount of motion, some kinetic energy, but the MC squared contribution to energy is much larger than the kinetic energy. And the particles aren't being created or destroyed. So as the universe expands, the energy density is dropping like the volume, right? 1 over the volume. So the universe expands by a factor of 2 in linear dimensions. The density of dark matter drops by a factor of 8, the energy density. But a cosmological constant, like the name implies, is constant. You can think of it as an energy associated with every cubic centimeter of space. So you create more space, you have more of this energy. So the mix changes over time. So there is so even with the cosmological constant, there's still a cosmological constant contributing some to the energy density at this time. It's just too small to be shown on this graph. But to answer your question, that's if it's a cosmological constant. One of the possibilities is that it's not, and so that there actually is some dark energy still present even at early times, and that could potentially resolve the crisis.
Yeah, yes, I don't even know if this question is more semantics or if there's something deeper, but I've heard the expansion of space referred to as a stretching of space and as creation of space. Is there any important difference between those two concepts?
I don't think so.
Okay.
Yeah. They're words to they're both us grasping for words to describe what's going on. And I think that those are attempts to describe the same thing.
This is all super interesting. Can you say anything about experiments that are taking place now that will help understand the discrepancy and maybe lead to some answers?
Yeah. So in fact, James Webb, I think is going to be helpful on this front. So Wendy Friedman, who I mentioned earlier, is she's using James Webb to measure Cephieds in these nearby galaxies that are the ones that host that have supernovae that have been recorded, right? So these Cephieds that are being used to calibrate supernovae. And she says with James Webb, she's already getting, she also has access to the Rees et al. Team's data, which is all publicly available in the Hubble Space Telescope archive. And she says that with the Webb data now, this period luminosity relationship they can get with Webb has half of the scatter. So they're able to see a tighter relationship. And if you reduce the noise that there is in that relationship, it just makes it easier for you to find any systematic things that might be lurking in there. And so Webb is really valuable there. I also think it's really valuable that an independent team is doing the very hard work of going back to the raw data and doing their own analysis on it. And we could very well see progress from that. I've done some work, my students have done some work with their data. A number of people have, but I always started from their measurements of the photometry of the Cephieds. And actually figuring out how much light is coming from a Cepheid, taking that from the image data itself is challenging. And these can be in crowded fields. It's not the only star whose light you're picking up. Crowding is a factor. And so anyway, I'm really happy that a different team is going in and starting from the raw data, which is something that we couldn't do.
Yeah. Has anyone tried to unite modified Newtonian dynamics with dark energy, dark matter? I know a professor of physics at Berkeley, and he said that really, it's not a theory. It's just like a calculation. And I'm just wondering if anyone's working that way to find an overarching theory that would explain why neither theory can explain everything. I don't know. Maybe you could tell me.
Yeah.
You're the expert.
So MOND is modified Newtonian dynamics. It's an attempt to explain cosmological the cosmological observables that lead us to a conclusion that there's dark matter. It's an attempt to explain that by changing gravity. Instead, it's properly, so it is. There are interesting things that MOND, about galaxies that MOND seems to explain quite well. Meaning that, wow, this one simple change has a lot of explanatory power for galaxies. It doesn't work so well on other scales. It wasn't able to, you couldn't use this to make predictions of what you'd see in the microwave background. Now that we know what we see in the microwave background, people have been able to apparently claim that they can now predict that. There are some efforts to find out how MOND can emerge from a relativistic theory of gravity. So taking some things we think from our experience with general relativity are definitely properties of space and time, and preserve those while we modify the theory of gravity. Those end up being extremely complicated, and you lose some of that virtue of MOND, which was its simplicity. And you end up thinking, wow, dark matter is a much nicer explanation than that. So yes, there is effort to kind of figure out how this MOND idea, which is an interesting idea, as explanatory power on galaxy scales, to try to understand, well, can we get that out of a relativistic theory, and one that can then predict a bunch of other observables, and possibly even, think the accelerating expansion that we usually connect with dark energy. Yeah, so efforts like that are underway. They haven't. The bottom line is they've ended up looking really complicated, and no one's been interested in them. I mean, almost no one's been interested in them.
So I have a question or two. One of them is, the whole notion of the Hubble constant was predicated on the fact that you had a fairly constant universe, or at least somewhat constant. And is that now obsolete since we know it's not?
So,
So is there a need for a Hubble constant, I guess is the question,
oh,
since the universe is not?
it's not. Let's see if I escape from this. I've got. So this expansion rate is certainly not constant.
Mhm.
And in fact, this is lambda CDM with its parameters fit with the Planck CMB data. And that's the prediction of the model for the expansion rate as it's changing over time.
Mhm.
These are kind of strange units, but remember, kilometers per second per megaparsec. If you divided the kilometers by the megaparsecs, it just has units of inverse time.
Mhm.
So anyway, you can think of it as inverse seconds. Like, how much does the universe expand every second? Well, by what fraction does the universe expand every second? Today, the universe expands by about 10 to the minus 8, by 1 part in 10 to the 18 every second.
Mhm.
Okay. Back when the universe was in some sense 1 billion times smaller, back when, well, so between this time and now, the universe has expanded by a factor of 1 billion in each linear dimension. At this time, right, the rate of expansion, so the universe increased in size by 10% every second, expanding much more rapidly. Is this variation in time what you're talking about when you're
I guess that's what it is. In other words, as your horizontal axis shows, that is the Hubble constant, but it's not
right? So
constant.
today, so this is the right. So right here, this is the Hubble constant.
Mhm.
So and the word constant here means constant in space,
Mhm.
constant spatially.
So
So,
if space is changing, then of course, obviously the constant changes.
well, yeah, so as the universe expands, as the universe is expanding through here, that rate of expansion is changing.
Mhm.
At least viewed with, once you coarse grain the universe and think about it just on very large scales, it's very homogeneous.
Mhm.
And that uniform expansion appears to be a good approximation. So that at any point in time, the universe is, and viewed on large scales, the universe is expanding at the same rate everywhere.
Hmm.
So that's the sense in which it's constant.
Yes.
Okay. A spatial constant.
Mhm. All right. Gotcha. Anybody else have a question? Okay. The only other question I had was in covering the microwave background, I know that we probably have holes in that spectrum of wavelengths that we've been able to examine. So for instance, in the terahertz region, that's very much shorter than the microwaves that you're looking at normally.
That's right.
But it's not light either. So it's
Mhm.
kind of this gray zone. And is there any information in there that we might glean, or is there not very much of it there to worry about?
So the temperature, the temperature of the microwave background today
Mhm.
is about 2.7 Kelvin. It's a black, and the spectrum is that of a black body of just, it's a thermal spectrum, and it peaks around around millimeter wavelengths, and out at or wait, so you want to use frequency, so around 100 gigahertz or so.
Yeah.
Okay, and that's because of that temperature. Anything with that temperature is going to peak at around 100 gigahertz.
Mhm.
Out at a terahertz, the flux of light from this is greatly suppressed. So
Okay,
it's so
got it.
it's
Yeah. So it's very difficult, and it's not
very
probably
difficult to
not-
measure it.
It's
And then
probably
there's
not worth going after
and it-
because it's such a small part of the.
that's right, and it's subdominant to light from, that basically has been created by stars and then reprocessed by dust into that wavelength range.
Yeah, which is why the web is so important, because it's covering them a little bit more it's nudging into that a little bit, so. Okay, got it. Anybody else? Okay. Well, thank you very much, Dr. Knox. Thank you all. Okay, what do we got here? We've got a question that says, a young person has just asked, is the law of conservation of mass still true now? Conservation of mass still true.
There's not really a distinction
Well, he's
between
got-
mass and energy, so no.
Yeah, I was gonna say, yeah, exactly right. Yeah, in other words,
Oh, yeah.
you have to know that mass is equivalent to energy and vice versa. All right. Good night, all. Thank you very much for joining us. Where am I at? Where's my recording?
Turns things off.
Yeah, just a second. Oh, here we go.